Okay, hello everyone. Thank you for joining my session toward Cross-Hypervisor test framework for VirtIO Backend validation using VirtIO CTS. Before moving to the presentation, I'd like to briefly introduce myself. So I'm Kazuki Kuzu from Panasonic Automotive Systems and a member of Automotive Grade Linux SDV expert group. And I have been working on embedded system and hypervisor related tasks for 5 years. And for my private life, I will introduce myself briefly. I love fish game, and I like skiing, meat, whiskey, and green tea. Okay, so now let's move to my presentation. Okay, here is today's agenda. First, I will share the needs for SDVs and virtualization in the automotive industry. Next, I will explain what VirtIO is, a key technology for SDVs. Then, I will introduce the newly developed VirtIO Conformance Test Suite for VirtIO. First, regarding the necessity of SDVs and virtualization technology in the automotive industries. The term SDV has become a common keyword in automotive development. When the SDV concept is realized, shifting development focus from hardware-centric to software-centric approach will enable various new capabilities. To give a few simple examples, connecting vehicle to networks allows their onboard software to be updated to the latest version at any time. Furthermore, connecting to the cloud enables the additional of feature previously impossible on a standalone vehicle. It also allows for the reflection of individual settings even in the sharing vehicle, such as those used in car sharing service. While these convenient features become possible, they also lead to a rapid increase in software code. This means the proportion of software within the automotive industry's revenue is expected to grow. In this environment, enhancing software reusability becomes an even more critical challenge than before. And another changes in automotive architecture is a shift toward high-performance computing (HPC) for in-vehicle ECUs. Previously, ECUs were distributed separately for each individual function. However, modern vehicles now carry numerous ECUs, leading to issues such as limited space and difficulties in managing and updating individual software. Consequently, vehicle architecture is evolving toward HPC, where one or a small number of high-performance ECUs handles multiple functions. To run multiple functions and operating system on a single hardware platform, hardware virtualization is required. And a virtualization platform fulfills this role. Through the abstraction provided by the virtualization platform, the operating system accesses virtualized device created by the platform rather than directly accessing the actual hardware. The ARM architecture, commonly used in the automotive applications, offers robust virtualization. Hypervisor leverage these features to virtualize CPUs and memory. Conversely, peripherals like block and net and so on along with multimedia devices such as GPUs and audio components, require separate virtualization method. In this presentation, I will use the term virtualization platform, both concepts including hypervisor and device virtualization, as well as VM lifecycle manager. A virtualization platform provides several virtualization methods, such as full virtualization and para-virtualization. Full virtualization emulates the CPU and devices, allowing the guest OS to operate as if running on a physical hardware. However, this requires the overhead associated with device emulation. Para-virtualization incorporates modifications that allow the guest OS to recognize it is running in a virtual environment and communicate with virtual devices. Compared to full virtualization, the guest OS requires adaptation for virtual devices. But since device emulation is unnecessary, the overhead when using device is reduced. The device virtualization enables device multiplexing and abstraction. This page lists several cases where the OS access devices. The leftmost diagram shows bare metal without a virtualized environment, where the OS driver directly accesses the device. The diagram to its right shows a virtualized environment, but device access is bound to a specific guest via pass-through. So it is fundamentally not significantly different from the bare metal case. The two diagrams on the far right shows environments using virtual devices, as explained earlier, with full virtualization and para-virtualization side by side. Both have drivers that operate the actual devices, with virtualized or emulated device existing within the virtualization platform. The guest operating system accesses a driver to access these virtualized devices. Compared to non-virtualized environment, virtualized environment allow multiple OSs to utilize devices. Furthermore, guest operating systems no longer require drivers to access physical device. Thus, guest operating systems are decoupled from the actual hardware by device virtualization. I explained that virtualization decouples the guest operating system from the hardware, but dependencies between the guest operating system and the virtualization platform may still remain. A solution to this is the VirtIO standard interface for virtual devices. In the left diagrams, guest operating system 1 accesses virtualized device A using a proprietary interface. Guest OS 2 accesses the VirtIO device X using the VirtIO interface. Attempting to reuse this environment in the next generation, but with a changed virtualized environment, result in the scenario shown in the right diagrams. In the next generation, the virtualization device used by guest operating system 1 has been replaced from virtual device A to virtual device B. Since guest operating system 1 has the driver for virtual device A installed, it cannot be used as is. In contrast, guest operating system 2 uses VirtIO. even if implementer or provider of the VirtIO devices changes. It uses the standard VirtIO interface, allowing it to continue operating without modification. In this way, VirtIO enhances software reusability. It is a crucial technology in an era where the amount of development code is increasing, as well as we see with SDVs. So what is exactly VirtIO? VirtIO is a specification for virtual I/O device defined by the OASIS standard organization. VirtIO is currently available in version 1.2, with version 1.3 and 1.4 under definition. According to the specification document, VirtIO is a straightforward, efficient, standardized, and extensible mechanism for virtual devices. VirtIO was initially used in the server industry, particularly for virtualizing components like networking and storage. The shift toward SDVs and HPC in the automotive industries created demand for multimedia VirtIO, such as for GPUs, sound, and camera, which was not previously required in the server industry. This diagram shows the flowchart for how VirtIO standardization is being defined with OASIS. Along with a list of VirtIO devices needed by the automotive industry, Panasonic Automotive Systems is promoting the adoption of VirtIO within the automotive ecosystem through its application to Android and Azure. This page provides a brief overview of VirtIO configuration. This diagram illustrates the configuration with a guest operating system running on the hypervisor uses VirtIO. Typically, when an application uses a device, it utilizes a device driver. Similarly, in a guest operating system using VirtIO devices, application uses the VirtIO device driver. The difference is that the VirtIO driver does not directly manipulate the actual device. Instead, it sends requests to the VirtIO device on the host OS. The VirtIO device then executes the processing using the physical device's device driver, just like a regular application. From the guest operating system's perspective, the VirtIO device is recognized just like a physical device, with the only difference being that its driver is a VirtIO driver. The transport layer protocol, PCI, MMIO, and channel I/O are defined as a communication path between the driver and the device for device initialization and operations. Additionally, shared memory and VIRT queue are utilized to request processing. To repeat from the guest operating system perspective, the VirtIO device appears as a physical device, and it does not recognize the actual underlying devices. This means VirtIO communication is independent of the specification of the actual physical device. Consequently, the guest operating system only needs to communicate with the VirtIO device, and it does not need to care about the actual hardware. Put another way, regarding of whether the actual hardware is cloud infrastructure, automotive hardware, or even a Raspberry Pi. The hardware can be treated as a virtual device that is accessible through the VirtIO driver. Azure also uses VirtIO as one implementation method for SDB. I saw this diagram in various places at OSSJ this time, and I will use it here as well. So it shows the SODEV architecture utilizing open source software as advocated by Azure. The DOM-D of the Zen hypervisor has VirtIO Backend, which includes components like VirtIO device. The guest and functional domain contains the box for the VirtIO frontend, which includes the VirtIO drivers. While SODEV itself is a concept starting in 2025, Azure has long provided an image utilizing VirtIO and can be built on Yocto system using the VirtIO ARC64 machine type, or QEMU x86-64. And here is a diagram from the keynote at the last year's 2024 Azure All-Member Meeting. In traditional automotive development, hardware was developed first, and then software was made for fit that hardware. In SDV development, the volume of software development increases significantly. The traditional approach of constantly redeveloping software to fit new hardware become unsustainable. Introducing VirtIO here allows for hardware abstraction. This enables continuous development of the latest software in the cloud, decoupling it to the necessary hardware at the required time. By leveraging VirtIO for SDV development in this way, automotive development can evolve from a hardware-first approach to a software-first approach. While I have outlined VirtIO's advantages, a concern in automotive environment is implementation diversity. As shown in this part of the OASIS VirtIO specification, VirtIO aims to provide virtual environments and guests with a standardized virtual device mechanism. However, the strict requirement unique to automotive applications may require environment-specific implementation. Key in-vehicle requirements include long product life cycle, limited computational resource compared to servers, and strict performance requirements. To address these platform-specific extension, implementation of undefined device or different version may be used. While this may be done to meet product specification or optimize functionality, they ultimately impact long-term software portability and compatibility. So we are currently developing the VirtIO Conformance Test. The VirtIO Conformance Test, VirtIO CTS, verify the conformance of VirtIO device to the OASIS specification. These tests run from the guest perspective, confirming that the device implementation behaves as expected by the specification. The tests are loaded and executed like a normal guest and are designed with a minimal set of requirements, so they can be executed on any hypervisor without hypervisor-specific configuration. Currently, the VirtIO CTS is being developed in collaboration with Linaro and is planned for release as open source software. Utilizing this VirtIO CTS allows verification of a VirtIO device's compliance with the specification and provides visibility into its portability. It also improves software quality when used as a test during new VirtIO device development. The current VirtIO CTS consists of two types of tests, one using a unikernel and another using a rootfs image. This page provides a more detailed explanation of the two types of tests. The test environment, as shown on the left side of the diagram, involves a guest operating system running on a virtual environment using VirtIO devices. First, unikernel performs basic VirtIO compliance verification test. A unikernel refers to a minimal, single-purpose kernel designed for lightweight testing. It requires no file system or user space component and performs boot VirtIO devices detection and basic compliance verification test. The test test results are output via serial port in a test anything protocol format. It can also run in a UEFI environment and is executed on any ARC64 hypervisor. The tests are written in Rust and implemented as a framework in a form that facilitates implementation and extension. Additionally, there are tests using rootfs image. The rootfs image is a root file system for Linux ARC64, usable with the latest kernel version, enabling testing of complex device that requires user space test. The rootfs image provides a complete user space stack for ARC64 Linux, enabling tests like GPU testing via the Mesa 3D libraries. It also includes application for measuring hypervisor latency. While numerous Linux-related test frameworks exist, VirtIO CTS is being developed from scratch rather than extending existing ones. To explain the reason, I have summarized the object of the respective test, but I will skip the detail of each test here to keep things simple. If you are interested in the details, please refer to the uploaded materials. The main point is that VirtIO CTS is unique in verifying VirtIO device without relying on hypervisor or other components. Now, I'd like to show you an example of the actual test result in action. While the test can run in any virtual environment, I'll demonstrate result from QEMU with it easy to access. The upcoming VirtIO CTS repository will also include instruction for running tests in QEMU. The execution environment used here is a host PC with an x86-64 architecture running QEMU version 10.0.2. Additionally, TCG is utilized to run an AX64 image on the x86 64 host environment. The actual QEMU setup command is shown on the slide. While many VirtIO devices are specified for use, the key point to note is highlighted in red. The VirtIO Test Suite binary is specified via kernel option. And here is an example of the execution output. It is output in tab format, sequentially executing tests for each detected VirtIO devices. And this page shows the relationship between each test result and the OASIS specification. Each test result verifies whether the VirtIO device operates according to the OASIS VirtIO specification. VirtIO CTS focuses specially on the VirtIO device, confirming that the device side requirement defined in the device specific section of the specification are met. On the left, you can see an example from the VirtIO GPU section. While there is more detail available, I'm showing the level of detail due to slide space limitation. On the right, you can see an example of the GPU test tab output, which explains how each section matches the test result using unikernel. Next, I present an example of the result using the rootfs images. The rootfs image utilizes an existing Linux kernel. This time, I use a pre-built version for AGL's VirtIO AX64 machine kernels. The host environment and QEMU version are the same as when running unikernel, with the rootfs test image specified in the drive option. And here are the test results obtained using the rootfs image. The VKMark performance at the top shows the output from running the standard VKMark benchmark application. By running similar application on other hypervisor environment using this rootfs image and the Linux kernel, it becomes possible to compare performance results on the virtualization platform while keeping the get side as an identical component. The lower hypervisor latency section is a test that can only be run when the Linux kernel has eBPF enabled. It measures the latency for each VirtIO command and summarizes the result. In this example, it measures the time for each VirtIO GPU command executed during VKMark. Similarly to the VKMark result, running this on other hypervisor environment, let us compare the latency during VirtIO command execution. And finally, a summary. The key term in the automotive industry include SDV for development style and HPC for architecture. In the SDV era, where software reusability becomes increasingly important, using VirtIO can enhance software reusability across vehicle model and generations. However, there is a concern that implementation that do not follow the specification for automotive use case could weaken VirtIO's advantages. To address this, we are collaborating with Linaro to develop VirtIO CTS, a conformance test suite for VirtIO device implementation. VirtIO CTS contributes to the long-term portability of automotive software and enhance the quality of software implementation. We plan to release VirtIO CTS as open source software, hoping it will contribute to improving VirtIO quality not only the automotive industry, but across the entire ecosystem. Okay. And that's all my presentation. Thank you. So does anyone question?
Thank you very much for your presentation. And at first, so I think so your slide is very good also for education for our younger generation engineers. Yeah, very good. And here my question is so in my understanding, so I felt VirtIO CTS is mainly intended for the VirtIO front-end drivers. And here my question is it possible to test the VirtIO backend drivers or the maybe daemons, user and daemons?
Okay. So currently, this unikernel test is targeting check the VirtIO device. So target is a VirtIO device.
Device. So
Yes, backend.
Backend. Yeah. Sorry, I was misunderstanding. Thank you.
VirtIO front end is a driver.
Yeah. Yeah, now it's clear. Sorry, I was misunderstanding. Thank you. Yeah, and also, so you showed us the rootfs image test also, and so there you added a bunch of VirtIO. So these are backends, I think.
Yes, this option lists the VirtIO device.
And does this does VirtIO CTS test all the VirtIO devices listed here?
Honestly, currently we have only 6 devices for testing: block, net, GPU, SUMI, console, VSOC.
Yeah.
So
okay.
if I will add another new VirtIO devices not listed previous devices, then we can't check the VirtIO compliance.
At the moment, how many supported VirtIO devices are listed in this test case?
In this case, the first block, sound, input, and console, and
maybe I guess all the supported VirtIO devices are listed, and also VirtIO CTS tests all the configured supported devices.
If
can I understand like this?
I don't forget the listed of all the target device when I creating this slide. That is all listed.
Yeah, it's okay. Thank you very much. It's clear.
Okay, thank you.
So my question is, first question, my question is, have a plan to provide the reference VirtIO supported kernel for this CTS test? Because your answer is a unikernel test to the backend, and this one test to the front end. But in typical case, created the front end kernel in myself. So it causes many misconfiguration. So if you provide the reference kernel, I can easy to debug.
Okay, so that is very important point. But okay, so here is some another test suite, and sometimes Linux kernel, Linux driver can be tested in the KUnit test or other Linux test tool. But the VirtIO device seems black box from the guest operating system perspective. So currently we are focusing on the VirtIO backend device test. Okay, and hopefully we have the reference implementation for Linux kernel drivers.
Yes.
Already, I think the problem is the configuration.
Yes, right. If this test developed as a kernel 6.5, so I want to use a 6.20. So I need to change. I created my own kernel, but VirtIO configuration is correct or not correct. It can test.
So,
Yes,
okay. Honestly, currently we are not targeting for the front end, so the unikernel is not the Linux kernel, and so how to say?
This is testing backend.
yeah,
So, okay,
yeah,
so-
it's understanding. Yeah.
If Azure can provide the reference, that is very helpful.
Oh, it's a good idea. Let's collaborate.
Let's collaborate with us.
Yeah, thank you.
Yeah, thank you.
Hello, I have one question on page 27. How did you measure the hypervisor latency, like eBPF or GenTrace?
Okay, so the hypervisor latency is measured by checking the the time, how many time spent for the VirtIO queue is used. If we want to request some command, we have to make header with this current of the VirtIO command and put it into the available link, and the device can handle it. After that, we can check.
Maybe you can use it that way to point where to where.
Where to where? Oh. Okay, so sometimes the VirtIO driver sets the VirtIO command and pass it to the VirtIO backend side and return the kick command. So honestly, this command are many times called in VKMark. So we can huge time the latency time. And after finishing the benchmark test, we can calculate the mean of the how many time is used that function.
Okay, thank you.
Hi, I have two questions. The first one is, do you have any plan to add the performance index to the device testing?
Sorry, could you say that again?
Okay. Currently, CTS only support the functional testing, right?
Yes, currently we are in the unikernel test. We are implementing the functional test.
Okay. But in the future, do you have any plan to add the performance test?
So honestly, we are currently considering adding the performance test. However, it's a little bit difficult for us to how many latency is okay for the virtualized environment. So currently we are investigate how to define the performance
Criteria.
Yes,
Okay,
criteria.
I got it. Okay, and my second question is this CTS extendable for especially for silicon vendor to add their own test before the device have been standardized by VirtIO? Is it doable?
So your question is Can this VirtIO CTS is used for the test before upstream some VirtIO device?
Yeah, can it be extendable by silicon vendor?
Extendable, so. Okay, sorry. Yes, we have the framework for making this tool, so third-party vendor can also provide after we are publishing open source.
Okay, thank you.
Okay, thank you. Okay, so that's all for my presentation. Thank you, everyone.